So in section 5.6, we're going to do a couple of applications of multiple integration, both double and triple integration. Here we're calculating centers of mass of two-dimensional regions and three-dimensional regions, and moments of inertia, similarly of two and three-dimensional regions. In terms of emphasizing, de-emphasizing, just really for the sake of time and the sake of focus, I'm going to de-emphasize moments of inertia and really focus on centers of mass. Moments of inertia appear in physics applications, engineering applications. Centers of mass actually also are physics, engineering, also appear in statistics applications because a lot of times density functions, which we often sort of use the metaphor of mass to think about, are also can be thought of as probability density functions, and centers of mass are a kind of average value related to some probability density function. So you'll see centers of mass occur in statistics. If I had to choose one or the other, I sort of lean towards centers of mass. I've actually done research in the mathematics of centers of mass. It's very closely related to some of the work that I do. So that's that. Big objectives here are to be able to compute centers of mass of two and three-dimensional objects, and that's essentially it. Largely a computational section, just like the others, and really an opportunity to bring to bear all that you've learned about constructing two and three-dimensional integrals. And the other thing that's going to happen here is you're going to have the opportunity to choose which coordinate system you should be integrating with respect to without really any kind of instruction at all. You're just going to look at the set and you're going to say, hey, this has a kind of cylindrical nature to it. Maybe I'll use cylindrical coordinates, or it seems to involve spheres. Maybe I'll use spherical, or maybe it's just fine in rectangular coordinates. So the goals, the big ideas, I think we've covered that. Let's hit the flyover here. I'm not super interested in the derivations of these various formulas at the moment. I think I just want you to kind of memorize these formulas, and we'll move forward from there. I will talk sort of heuristically about some of these quantities, but not really dwell on the derivation. So for example, the center of mass in two dimensions, if you were to take a two-dimensional set like this blue set here that we see in the figure, one might ask oneself, what's the balance point of that set? And so you could cut it out of the piece of paper and you could kind of move it around on the point of a pin or something, and eventually you'd figure out where it balances. And that's useful information. It comes up in engineering applications quite a lot. Another thing that you might add to the mix to make things a little bit more interesting is maybe the shape that you're looking at is not of a uniform material. Maybe it's made up of a mixture of different materials that are kind of glued together somehow. The stuff that we're going to talk about today is capable of still finding this balance point, even if, say, the material over here is far lighter than the material over here. So we're going to call that a density function, and essentially what it does is it tells us the mass density per unit area in the case of two dimensions, or the mass density per unit volume in the case of three dimensions. Okay, there are two sort of intermediate quantities that we need to understand before we get to the location of this point P, which is the center of mass. This might seem like a typo, but in fact the x and y coordinates of the center of mass are given by these two quantities. My is the moment of this shape about the y-axis. Mx is the moment of the shape around the x-axis. And what my is telling us, this notation, it's telling us sort of as this figure sits in the xy plane, and you could pretend that sort of gravity is acting into the plane. How much does this figure want to twist the y-axis, and how much does it want to twist the x-axis? Twisting y, twisting x. Twisting of the y-axis, the tendency for it to twist the y-axis is what we call my, the moment about the y-axis, and the tendency to twist the x-axis we call mx, the moment about the x-axis. Now, the tendency to twist about the y-axis actually depends on how far you are from the y-axis, and that is given by the x-coordinate. So there's this weird kind of reversal. The moment about the y depends on the x-coordinate. The moment about the x depends on the y-coordinate. And that's why we see this weird transposition that the x-coordinate of the center of mass depends on the moment about the y-axis, and the y-coordinate of the center of mass depends on the moment about the x-axis. So I just want to get that in the foreground because it can be confusing. The formula for the moment about the x-axis, which is discussed here, is, gosh, I thought it was highlighted here. Let me keep going. Here we go. So the formula for x bar and y bar is given by the formula for my over the mass and the formula for mx over the mass. Now, there aren't going to be any shortcuts here. When you're computing the center of mass, you're going to have to compute 3 integrals. These 2 integrals in the numerator are different, and then there's another integral in the denominator that's the same. So 3 total double integrals, a lot of work here. That's why in this particular section I'm really going to be emphasizing the use of the computer, and we'll be doing a lot of these calculations in Sage. So I want you to memorize this, that the moment about the y-axis is x times the density dA, and the moment about the x-axis is y times the density times dA. And the centers of mass are then these moments divided by the total mass of the figure. In this case, we compute the total mass by computing the density, computing the double integral of density over the area. And if you think about units, right, rho is mass per unit area times a little piece of area. What this is going to give me is a little piece of mass, and we're going to sum up all those little pieces of mass over the entire region R, and that'll give us the total mass of the region R. So this figure in the denominator, little m, is the mass of the region R according to this density function. In this situation, we call x bar, y bar, that coordinate pair, we call that the center of mass. If, as is often the case, we set rho equal to a constant, or even better, we set rho equal to 1, then the center of mass is also called the centroid. The center of mass is a more physical object because there's this mass floating around. The centroid, where we set rho equal to 1, constant density, the centroid is more of a geometric object that I personally have worked heavily with and find very fascinating. Okay, so finding the center of mass for a figure, let's look at example 5.57. Here you're given a region that has, it's essentially a triangular region with these 3 vertices, and you're asked to find, oh, and it has this density function xy, and you're asked to find the center of mass. So the first thing that you want to do is understand this figure. You're going to want to plot these 3 points and then figure out how to describe the region of integration. This isn't as fleshed out as I had hoped. We'll look at some more fleshed out examples in a bit. But essentially what you would have to do is set up the double integral for the numerator, the double integral for the mass, and the double integral for this numerator, and then you already have the mass. Plug all that in and you get these values. Turns out here 6/5 is the location of the center of mass. Okay, there's another example. finding mass, moments, and center of mass. So again, another example. I'll leave these to you to read. Just note here, here's one with the centroid. Find the centroid of the region under the curve e to the x over the interval 1 to 3, like this. So here's the region above by the curve, below by the x-axis, left x equals 1, right x equals 3. You're finding the centroid. You're assuming that the density is 1, and that has some geometric information associated with it. The other big application from this section is moments of inertia, and this is really just kind of telling you the inertia of this particular body with respect to a certain axis. And we can compute the inertia with respect to the x-axis by this formula, and the inertia with respect to the y-axis by this formula. And in fact, we can actually get the rotational inertia, the inertia with respect to the origin in the xy axis by adding these two things together and getting x squared plus y squared times the density. If you look on the right-hand side, each of these is just some double integral that you would be asked to construct and evaluate. All right. I'm not going to spend a whole lot of time on centers of mass, moments of inertia in 3 dimensions. The generalization is pretty straightforward. The only difference is we have double subscripts on the moments, and now we're measuring the moment with respect to the xy plane, the xz plane, and the yz plane, the 3 coordinate planes. The moment of this body Q with respect to the xy plane, of course, depends on its distance from the xy plane, and that's measured by the z coordinate. So that's why for mxy we see the z coordinate here. For mxz we see the y coordinate, and for myz we see the x coordinate. Once you get that straight, in other words, an easy mnemonic is the variable that's sitting here in the integrand is the one that's missing from the moment notation. So we have x, y, z is missing, and that's because it's over here. The center of mass of the object is the moments of the 3 moments divided by the mass of the object. You can compute the mass of the object by simply computing this triple integral without this extra factor of x, y, or z. Just integrate rho dv. Again, rho is mass per unit volume in this case, times dv, a little piece of volume. We get a little piece of mass. This triple integral gives us the mass of the body Q. All right, similarly, we have moments of inertia about the 3 axes, and they're given by these expressions. Finding the mass of a solid is simply integrating rho over the region Q. So you set up the integral, you use this as the integrand, and that gives you the mass. Moments of inertia, similarly, and this leads us to the collection of exercises. All right, the first exercise we want to talk about is exercise 298, and the instructions for this exercise are to find the mass of the region with this particular density function. So the region is this triangular region determined by these 3 vertices, and the density function is x plus y. So it's up to us now to construct the double integral r rho dA. All right, the first thing we have to do is describe r in terms of limits of integration. I think it's best to integrate in the y direction first, because I'm always moving from the bottom curve to the top curve like that. If I were to choose the x direction, up here I would be going from the y-axis out to this curve, but down here I'd be going from the y-axis out to a different curve. That would force me to use 2 different integrals. So definitely going dy first, then dx is the right move. Let me put the density function in there, x plus y. To determine the limits of integration in the y direction, we're going to have to come up with the equations of these 2 lines, L1 and L2. L2 is pretty straightforward. L2 is just y equals x, even though the scale doesn't look like it. L2 goes through the point 0, 0 and through the point 1, 1, and that line is, of course, y equals x. A little more complicated is the line L1 that goes through the point 0, 5 and 1, 1. So we first need to compute the slope. That's going to be minus 1 over 4. And then we take the point, one of the points, and the slope, and plug it into the point slope formula. We get y minus 5 equals minus 1/4 times x, or y equals minus 1/4 x plus 5. So now we have the lower and upper limits of integration in the y direction, x and minus 1/4 x plus 5. We've dealt with that y direction. Now we take this integrand and this region of integration, we squash it down onto the x-axis, and that's going to cover this portion of the x-axis. That'll give us the lower and upper limits in the x direction, 0 and 1. This is an integral that you could do by hand, but it's actually still somewhat non-trivial, lots of fractions and calculations. So we'll jump over to Sage and do this integral electronically. So in exercise 298, I'm going to declare the two variables x and y. I'm just going to do the double integral all in one line as opposed to inner and outer. Here's the integrand, x plus y. We're integrating with respect to y first from x to minus 1/4 x plus 5, and then we're integrating with respect to x from 0 to 1. Doing this integral yields, after a bit of thought by the computer, and even more thought by the computer. Boy, it really takes Sage a while to get up in the morning. 13/25 over 96, not the prettiest fraction. And we can actually turn that into a number here, if you're so inclined, around 13.8. Again, you should know how to do this integral by hand, but feel free to use a computer if you want. Same instructions. Now R is the unit disk and rho is given by this seemingly complicated expression. I say seemingly because we'll find that this actually simplifies rather nicely. All right, so remember that the mass is this double integral over the region of rho dA. So again, our task is to build the double integral. Now I see lots of circular symmetry here, so I think polar coordinates are in order. So we'll try polar coordinates. I also note here that this is actually 3 times the quantity x squared plus y squared quantity squared. What tips me off? Well, I see this x to the 4th and y to the 4th out here, and then I see this cross term x squared y squared. The constants, I just factored out of 3, so I had x to the 4th plus 2x squared y squared plus y to the 4th, and hopefully that's going to jump out at you as being this perfect square. All right, so if I do polar coordinates, I'll integrate with respect to r first. That's a ray that starts at 0 and goes out to the radius of this circle. The unit disk has radius 1, so the upper limit is 1. To cover the entire unit disk requires us to go all the way around 0 to 2 pi. If we're doing polar coordinates, we automatically have a factor of r, dr d theta. And it remains to fill in the integrand or do the integrand in terms of polar coordinates. And because of my observation about this being a perfect square, we see that there's an x squared plus y squared in the parentheses, which we should recognize as being r squared. So this is 3 times the quantity r squared quantity squared. All right. There's no theta in this expression, nor in the limits of integration, so we can immediately introduce a factor of 2 pi for the theta integration. And there's a factor of 3 that just carries along from the constant in the density function. And we're left with r to the 5th, which we would integrate to get r to the 6th over 6 and evaluate from 0 to 1. That would lead us to 6 pi times 1/6, which is just pi. I think we're good there. Yeah. So there's an integral that you can do by hand. Far easier to do this in polar coordinates than to do it in rectangular coordinates, even though that's how the problem was presented. Okay, in the following exercises, again, we're in 2 dimensions. We have a shape with a density function. We're supposed to use SAGE to answer the following questions. Find the moments, calculate and plot the center of mass, and then use SAGE to locate the center of mass on the graph of R. Let's do this first for exercise 314, the so-called trapezoidal region determined by this collection of equations. Let's sketch. We have y equals 0, y equals 1, so that's there. Let's y equals 0, y equals 1. And we have, what else do we have? Y equals x. And we have y equals 3 minus x. So that's going to have a y-intercept up there and an x-intercept down here. Okay, so this is the region that we're interested in. Let's see, we are all okay with that? I think we're okay with that. Okay, so the region that we're interested in is, of course, this region. I'm thinking that we should integrate in the x direction first. Why? Because in the x direction, we're going to go from one curve on the bottom to one curve on the top over the entire span of this region. All right, so remember to compute mx, we need to compute the double integral over r of y. Don't forget that this is y dA. And we've decided that we're going to integrate with respect to x first and then with respect to y. So y dx dy, like that. All right, if we're going to do x first, we know that this curve is y equals x, and this curve is y equals 3 minus x. So that means we have to solve for x in terms of y. The lower curve is y equals x, or x equals y. And then the upper curve is x equals 3 minus y. All right, once we've accounted for the x direction, we want to squash this thing onto the y-axis. And that's going to cover this little section right here from 0 to 1. So we know that y is going to go from 0 to 1. All right, let's leave that there for a minute, and let me just note, you can note my process here. My is going to be the exact same integral. The domain isn't changing, so the limits of integration aren't going to change. The only thing that'll change for my is that the integrand will be x. And we're also asked to compute the center of mass, which means we're going to need the mass of this figure. Same thing, the mass it's the same region. Oh, am I dropping? Yes, I am dropping the, I have forgotten all about the density function. Apologies here. So here in the general integral, we have a row. In the specific integral, we have 2x plus y. And similarly here, like that. And then finally, m is just the integral of the density over the whole region, 2x plus y dx dy. Again, these are integrals that you could do by hand, but I'm going to leave that to you as practice, and we'll jump over to 𝘀 to get these various quantities. I'm going to pause for a minute and take a drink. Okay, that went more from a sip of water break to an actual lunchtime meeting break, but I'm back now. So as before I hit pause, we were going to compute each of these quantities in a 𝘀 worksheet, and then we'll do the visualization as is requested here in part C. So first let's do each of these integrals. Here is exercise 314, and here's me computing the moment about the y-axis. So here we're integrating x times the density function over the ranges that we decided. The moment about the x-axis is y times the density function, same limits of integration. And then finally the mass is just integrating the density function without this extra factor of x or y that you see in the moment quantity. We'll do all of these integrals simultaneously and print the results. Doing so, we see that the moment about y is this nasty fraction, m sub x, m, and then how do we compute x bar and y bar? That's x bar, remember x bar is the moment about y divided by the mass, and y bar is the moment about x divided by the mass, and that yields these two quantities. Again, just judging from these fractions, these are not integrals. You know, they're within your ability to do, but it looks like there's going to be a lot of fractions flying around, and so maybe using a computer is the best remedy for this. The last part of the problem is to create a visualization where we plot the boundaries of the figure in question, this trapezoidal region, and we also plot the point corresponding to x bar, y bar. So let me show you that. Maybe just a bit of a quick 𝘀 tutorial here also. Here we're plotting the function 3 minus x from 2 to 3. Let me go back to the sketch here. So this is the function 3 minus x, and we're plotting it from 2 here to 3 here, because we only really want this little segment here. Similarly, we're plotting the function x from 0 to 1. So that's this function, but we only really want it from 0 to 1. Then we plot the top of the trapezoid, that's y equals 1 from 1 to 2. 1 to 2 here. And then finally the bottom, which is y equals 0 over the entire x interval from 0 to 3. And then I just plot the point. And then 𝘀 lets me plot several plots on the same set of axes if I just take these plots, store them as variables, and then use the show command with plus signs in between each of the variables. So this is the plot L1 plus the plot L2 plus L3 plus L4 plus the point. And if all goes well, we should see a nice visualization of the situation. So this is the trapezoidal region that's described by the equations, and this is the center of mass. And you might wonder, well, why isn't the center of mass right here in the center of this trapezoid? You know, there's a lot of symmetry here. Why is it offset? And the answer to that is really in this density function. We see that the density, the mass of this thing depends on x and y. It depends on your location. And the bigger that x is, the denser this material is. And similarly, the bigger that y is, the denser this material is. So what we can expect from this is the large x values are all over here, and the large y values are all up in here, right? So the large x values are going to draw the center of mass towards them, and the large y values are going to draw the center of mass towards them. And in the end, what you get is this slightly off-center point. Now you might say, well, hey, 𝘀𝗾, this doesn't look like it's really being pulled north, towards the high y values. For example, here's 0.5. That's sort of halfway between the bottom and the top. But what you have to remember here is that it's wider on the bottom than it is on the top. So there's a lot more mass down here than there is up here. So it's actually tending to pull the point down, even though the y values are making it heavier up here. And then the mass is kind of symmetric about 1.5 here, and yet the x values are higher, so it's going to pull this thing to the right. So there is an actual geometric interpretation for the location of this thing, of this point, if you look closely at the density function. Continuing, same problem, different set, different density function. We see the set given by the inequality 9x² plus y² is less than or equal to 1. And I'm just grabbing my notes here so that I don't make a mistake here. All right. So what does this all kind of spell out? Let's make a sketch. All right. I don't know why those vertical lines get so wavy like that. A little buggy. All right. We have, if you look at this, this is the equation of some kind of ellipse. So let's look at the upper bound of this inequality. 9x² plus y² equals 1. And if we put this into the standard form of an ellipse, it looks like this. That's standard form. Standard form is useful because it tells us what the major and minor axes look like. So if I make this 1/3 right here, oops, if I make this 1/3, then this will be 1. And we can see that the minor axis is length 1/3 and the major axis is length 1. And so we get this piece of an ellipse. Why is it just the piece of an ellipse? Because we also have x bigger than 0. That's the right half of the plane, and y bigger than 0, that's the top half of the plane. Together, that's the first quadrant. So these two say first quadrant. And the density function looks like this. All right, what are we supposed to do? We have to find mx, my, and the mass if we are to compute all the various things requested. So let's do, I always do my first because that's the x variable. That's x rho dA, and we've got to come up with some limits of integration for this. All right, honestly, I don't think it matters a whole lot. I think I would integrate, just stare at this for a moment. Let's integrate in the x direction first. You know what? Let me think about this for a minute. Let's do the y direction. I think there's a teachable moment here. So if we do the y direction first, that means we're looking at paths that are parallel to the y-axis first. So we're going to go, come on. And we're going to go x, and rho is, of course, the square root of 9x² plus y², square root. And we're going to go dy dx. All right, dy. These line segments that are parallel to the y-axis, they always start at 0 and they always end on this curve, which we can actually solve for y, like that. Now that's plus or minus, but we're going to take the plus version, like that. And then we take this domain and we squash it onto the x-axis, and we see that the interval, or the range in the x direction, is 0 to 1/3. So if you look closely at this, we're integrating with respect to y and then with respect to x. And if you look at this integrand, the integral with respect to y is going to be challenging because there isn't a handy u-du pairing going on here. But if you look a little more closely, you see that there is a handy u-du pairing if we wanted to integrate with respect to x. So why not reverse the order of integration just to make that inner integral easier? So we'll reverse the order of integration to make that inner integral easier. So that's that. The integrand stays the same when you're reversing the order of integration. Dx, dy. All right, so if we're going to go dx, dy, then we're talking about lines, paths that are parallel to the x-axis first, and then we'll do the y integration. So if I'm going parallel to the x-axis, I'm always starting at 0, and I'm always ending on the curve, but now I've got to solve the curve for x in terms of y. Doing that, I get 9x squared equals 1 minus y squared. I can take the square root of both sides. 3x equals plus or minus square root of 1 minus y squared. And then finally, we'll divide by 1/3. And we'll take the positive solution because we're going to the positive side of the ellipse. So x is going to have an upper limit of 1/3 square root of 1 minus y squared. Once we've accounted for that, we of course take the domain and we squash it onto the y-axis, and we learn that the y range should go from 0 to 1. So there is reversing the order of integration for a practical reason, because now the inner integral is with respect to x, and I have a u-du pairing that I can do a u substitution on. All right, let's look at mx. I'm writing out these integrals because honestly setting them up is 90% of the battle. Now you might imagine that for the moment about the x-axis, where we have a factor of y in the integrand, that we probably should stick with dy first. So we're going to go 0 to 1/3, 0 to the square root of 1 minus 9x squared, and y, 9x squared plus y squared square root dy dx. So that would be the strategic integral for the moment about the x-axis. And last not least, let's talk about just the mass itself, because we need that to compute the center of mass. The mass itself is of course the integral of the density over the entire region. And pick one. Let's take this one. 0 to 1/3, 0 to the square root of 1 minus 9x squared, and then just the density function, 9x squared plus y squared to the 1/2 dy dx. No extra factor of x or y in this case. Let's jump over to Sage and use it to compute these integrals. I do want to make a note here, down here, this inner integral with respect to y, we've lost our nice u-du pairing, and reversing the order of integration isn't going to help because there's neither a factor of x nor a factor of y to save us. So this integral would be challenging. This integral would involve some kind of trig substitution in order to evaluate. With that said, let's jump over to Sage and figure out what these values actually are. So this takes me down to exercise 318. So computing m sub y, we're integrating our integrand x times the square root of blah blah blah, the density, and we're integrating with respect to x first and then with respect to y. For the moment around the x-axis, we have a factor of y in here, and then the density function, and then we're going to do dy first, and then we'll do dx. And then finally, for the mass, the inner integral is just the density function. Integrate with respect to y first, then with respect to x, and we'll show the mass. So let's execute all of those pieces. M sub y turns out to be 1/36. M sub x turns out to be 1/12. These might be integrals that you can actually do, given that these fractions are so nice. And then last, you do see this really complicated situation, which I warned you about, right? This doesn't have a nice u/du substitution, and it looks like it's not actually a trig substitution, but rather it's a hyperbolic trig substitution, because we see the arc hyperbolic sine sitting here as the intermediate value. Fortunately for us, we have ∅ to come to our rescue, and we end up with pi/18 for the mass. Pi/18. All right. We can plot this. We could compute the center of mass, which I don't think I actually did here. Let me put that in here. So let's show n of m sub y/m and n of m sub x/m. So we'll print out the decimal approximation of x bar and y bar. Remember, x bar is my/m and y bar is mx/m. I'm also going to do the visualization here. So I'll plot the ellipse over the just the x values that we're interested in, and I'm also going to overlay the point, a red point, at the location of the center of mass, and then I'll show both of those on the same plot. So let's do that. All right, we see that the center of mass is around 0.16, 0.48, 0.16 right about here, 0.48 right about here, and that's that. The blue trace is the quarter of the ellipse that we were dealing with, and the red dot is the computed center of mass. Great. Moving right along. Problem 334. So Q is the solid unit hemisphere. That's a sphere of radius 1. We want to find the mass if its density rho is proportional to the distance from the origin. So we need to first interpret that. Rho of x, y, and z, some point in space. The density is proportional to, so we introduce a constant of proportionality k. The distance that this point is from the origin, x squared plus y squared plus z squared to the 1/2. So there's the density function, and we constructed that based on the description in the problem. Now, if we want to find the mass of this unit hemisphere, we need to do an integral. The mass of this unit hemisphere, this is a hemisphere. We're now in a three-dimensional situation, so it's a triple integral over the set Q of the density dV. And we need to convert this symbolic representation of the triple integral into something that we can actually compute. Now we have a choice in front of us: Cartesian coordinates, cylindrical coordinates, spherical coordinates. Given that we're looking at what appears to be a hemisphere like this, I would suggest at least trying spherical coordinates to begin with. If we're going to do spherical coordinates, we need to convert the density to spherical coordinates. X squared plus y squared plus z squared is actually rho squared. Square root is just rho, so the integrand is k rho. And I'm mixing rows here. We should be careful. This row is the row of cylindrical coordinates, and this row is the row representing the density function. So just to be on the safe side, I'm going to convert this row to, oh, I don't know, what could we call it? We could call it eta. So in this case, eta is our density function, and rho is the radial variable of spherical coordinates. So the density function eta becomes k rho. Don't forget also to include the extra factors related to spherical integration. And then the order of integration, we'll try d rho, d phi, d theta. All right, rho is, remember, in the radial direction, and it starts at the origin and goes out to the surface. This surface is the unit hemisphere, meaning the radius is 1, so rho is going to go from 0 to 1. It's the hemisphere, which means in the phi direction, we only need to go from the angle 0 out to pi over 2. Remember that the full traversal from the North Pole to the South Pole is 0 to pi. We only need to go out to half of this sphere down to the equator, 0 to pi over 2. And finally, we need to go all the way around to capture the entire upper part of the hemisphere, 0 to 2 pi in theta. Okay. Well, as is often the case, the theta integral is straightforward. It's 2 pi because there's no theta dependence in here. There's a factor of k, a constant of proportionality that can come all the way out of the integral. We have a rho cubed there, which we can do separately. That turns into rho to the 4th over 4. When I plug in 1 and 0, I get 1/4. And the last thing to consider is the integral in phi. When we integrate sine of phi with respect to phi, we get minus cosine of phi. And that's going to lead us to plugging in pi over 2 and 0. We're going to get minus root 2 over 2 plus 1. So that expression altogether is the mass of this hemisphere using this particular density function. I don't remember if I did this one in Sage or not. Let me scroll down a little bit. This is problem 334, so no, I didn't bother. I guess the calculations were so straightforward, I decided not to use Sage. All right. Problem 339. Here we've got a t, so that suggests that we're going to use Sage. We have another solid, and the mass of that solid is given by this expression. This appears to be in cylindrical coordinates. We're going to use Sage to answer the following questions. Show that the center of mass of Q is located in the xy plane, and then graph Q and locate its center of mass. All right, we want to figure out, based on this integral, we want to sketch what this figure looks like. In r and theta, so if we focus on just the xy plane, we see r going out from 0 to 1, and we see theta going from 0 to pi over 4. So we're kind of looking at something like this. Let me sketch just part of a unit circle in here. And then theta is only going from 0 to pi over 4. So what we're really looking at in the xy plane is this little piece of pizza. And what's going on in the z direction? Z is going from the plane z equals -1 to the plane z equals 1. So this is really just a wedge-shaped cylinder that goes from -1 in the z direction to +1 in the z direction. So hopefully you can all kind of visualize that. The first task is to show that the center of mass of Q is located in the xy plane. What this really means here is we want to show that z bar is equal to 0. And we know that z bar is equal to the moment about the xy plane divided by the mass. So this is equivalent to showing that the moment about the xy plane is 0. Let's write down the equation for the moment about the xy plane. The moment about the xy plane is given by this triple integral. xy, the missing variable is z, times the density, dv, and the volume that we're talking about is q. Alrighty, now what is the density function in this situation? Well, if you look at this expression, one of these r's, so this is r times r, right? R squared is r times r. And one of these r's comes with the with the cylindrical integral. So the other r, this must be the density. So the density function in cylindrical coordinates, the density function as a function of r, theta, and z is just r. It depends only on r. All right. So that's helpful. Let's now re-express this integral in cylindrical coordinates. So we'll stick with cylindrical coordinates, largely because we have all of the pieces that we want. So we take z. Now in cylindrical coordinates, z is just z. So z goes along for the ride. The density we've determined is r, and then we have another r, dr, d theta, dz, like that. The limits of the integration are the same, 0 to 1, 0 to pi over 4, and finally minus 1 to 1. We can do this integral in any order, and notice that it's completely separable, so we can do the z integral. The z integral is going to be z squared. So let's look at the z integral, minus 1 to 1, z dz, times what's left behind, 0 to pi over 4, d theta, and then last not least, 0 to 1, r squared dr. I think I've got all the pieces there. Doesn't matter which of these we do first, and I would suggest that we do this z integral first. Why? Because that's an odd function over a symmetric interval. The function z is odd, and the interval from minus 1 to 1 is symmetric. So right off the bat, we can say that this is 0, and it doesn't really matter what this is or what this is. Doesn't really matter. The whole thing is 0, and we're done. We've shown that the moment about the xy plane is 0, therefore z bar is 0, and hence the center of mass in the xy plane. So we've done what we were asked to do in part A. Part B, graph Q and locate its center of mass. So here we have to do all of the work associated with finding the center of mass for a three-dimensional body. So let's talk about that. We need to find x bar, which is m y z over m. We need to find, let's just carry that out here. So that means we need to find m, y, z, which is going to be the integral, triple integral, same triple integral here, 0 to 1, 0 to pi over 4, and minus 1 to 1. But here we're doing the moment about the yz plane, so there's going to be an extra factor of x in there, and then r squared dr d theta dz. And you might be saying, hey, wait a minute, Schuller, there's no x's in a cylindrical integral. And I would say, you're right. What do we do with that x? We have to replace the x with the cylindrical coordinate transformation, r cosine theta. So I'm going to rearrange this a little bit and tuck that. In fact, let me just move this whole little bit out, and we'll replace this with r cosine theta. So that's secretly, that's the x from the moment calculation. So one has to be careful when you're mixing sort of Cartesian coordinates, right? All of these formulas for center of mass are given in Cartesian coordinates. If you convert them to cylindrical coordinates, don't forget to convert these Cartesian variables to the appropriate coordinate system. Y bar is, of course, mxz over m, which means we better figure out what mxz is. Same integral, minus 1 to 1, 0 to pi over 4, 0 to 1, y, and I'm going to leave a lot of space here, r squared dr d theta dz. And of course, we've got to convert that Cartesian coordinate y into the appropriate cylindrical coordinate, which is r sine theta. And then we just have to compute that integral. Last, z bar, we already know. Z bar is 0, so we don't have to do any work there. Now, lurking in here also is the integral for m, which we're given up here. Right, this is m. All right, I can't remember if I did this one in Sage or not. Let me double check here. Looks like I did this one by hand, so let's practice a little bit, do this by hand. All right, so let's look at MYZ here. Constant limits of integration, that's nice. DZ, no other z dependence, so I can do that integral and I get a factor of 2. R, I can integrate r cubed from 0 to 1, and I'm going to get 1/3. That takes care of dr. The last one is d theta, which means I have to integrate cosine of theta with respect to theta. That's sine of theta. Sine of pi over 4 is root 2 over 2. And sine of 0 is 0, so root 2 over 2. So this simplifies to root 2 over 3. Let me check my notes here. Excuse me. There was an r, extra factor of r here, that's r cubed. So it doesn't simplify quite as nicely as I'd hoped. It's not bad. The r integral, r cubed goes to r to the 4th over 4. That makes this a 1/4. And that makes this a 1/4. And I think that's good. All right, let's do mxz. Similar situation here. The z integral is going to contribute a 2. The r integral is going to contribute a 1/4. Let's do the theta integral. Now we integrate sine theta, we get minus cosine theta. Plug in pi over 4 and plug in 0. And it's a little less simple than the earlier one, but that's mxz. And then finally, let's do m, and we'll look up here for m. Let's see, dz is going to give me a 2. D theta is going to give me a pi over 4. So 2 pi over 4. And finally, the r integral, integrating r squared from 0 to 1 is going to give me 1/3. And that all nets out to, it looks like a pi over 6. Check my notes, that looks good. And then last not least, you can just plug these values into x bar, y bar, and z bar. Let me go over to Sage now. I do believe I've done the calculation for this. Yeah, I did do the calculation because I needed it for the visualization. So here are all the pieces, and you can see there's the root 2 over 4, and there's the slightly more complicated mxz. There's x bar, y bar, z bar. All right, and let me show you a plot. This plot was a little more challenging because it's a volume, and it's in cylindrical coordinates, so there's a lot of moving parts in this particular example. Here's me defining x bar, y bar, and z bar because I'm going to need those coordinates in my visualization. Here's me importing the sphere function so that I can plot this point in 3 dimensions using a tiny sphere. So I take a sphere of radius 0.05, I color it red, and I move that sphere to the location of the center of mass. And I call it PT, and I just add that to the list of pieces. Okay, you can see there's a lot of stuff going on here. This figure, if we go back to my sketch, it's got this wedge-shaped base on the bottom, a wedge-shaped base on the top. It's got this curved outer cylinder. It's got these two vertical faces along the sides. So I have to actually build all of those surfaces separately and then mush them together into a single figure. If I do that, I need my cylindrical coordinate system. For the top and the bottom, I'm looking at a surface z as a function of r and theta. So I define a cylindrical coordinate system. Z is height, r is radius, theta is azimuth. And then I plot z equals 1 over the cylindrical variables r from 0 to 1 and theta from 0 to pi over 4. According to this transformation, with a nice square aspect ratio and slightly transparent so I can see inside and see the dot at the center of mass. That's the top. The bottom is z equals -1, but over the same wedge-shaped region. R goes from 0 to 1, theta from 0 to pi over 4. That'll get me the top and the bottom. Now, I'm going to do that curved cylindrical side. There I need the radius as a function of z and theta. Doing that, I change this coordinate system. I shuffle these things around so that the dependent variable is here and the independent variables are over here. And then I plot the cylindrical side is r equals 1 for z from -1 to 1 and theta 0 to pi over 4. Now I'm going to do the two flat sides, and now I need theta, the azimuth, as a function of radius and height. I have one side, theta equals 0, r goes from 0 to 1, z goes from -1 to 1, and then I have the other side, theta equals pi over 4, r 0 to 1, z -1 to 1. I'm storing all of these in variables. I already talked about this point. I add all of those plot objects together and I'll render them. Eventually I'll render them. And there you have it. And if I rotate it around, you can see the top wedge, the bottom wedge, that outer cylindrical edge, the two vertical faces, theta equals 0, theta equals pi over 4. If we look down on top, we see that pizza-shaped wedge. And inside, at z equals 0, the xy plane, we see the center of mass. Okay? And that's the visualization. I'm going to save this worksheet on the Canvas discussion so you can download it and play around with it and adapt it to your own purposes. All right, in 345, we have another solid, and it has a constant density function, and you're asked to show that the moment xy, the moment about the xy plane is half the moment around the yz plane. So this is really an exercise in computing these two quantities and then demonstrating the desired relationship. So I think it's worth visualizing this figure first. This figure is x squared plus y squared between 0 and 16. Of course, it's always going to be greater than 0. What about the upper limit? What does that thing look like? Let's try to build a sketch. Oops. Got to draw straight lines here. Okay, the upper limit is x squared plus y squared equals 16. That's a circle of radius 4, like that. And let's just sketch that in there, like that. And we have x bigger than 0, y bigger than 0, so that restricts me to the first quadrant. And then finally, z is going from 0, the xy plane, up to the plane z equals x. So that's a plane that would kind of hit the xy plane here, and then it would kind of go up in this direction. Okay, and you have to kind of imagine that sitting above the xy plane here. This definitely looks like a job for cylindrical coordinates again, because this base has a lot of circular features to it, and the z component maybe doesn't so much. So let's start with the formula for mxy. The moment about the xy plane is the triple integral over the solid Q. Z is the missing variable, the density rho dv. And now let's fill in the pieces as if we're going to do this in cylindrical coordinates. In cylindrical coordinates, z stays z. Rho is just this constant k. We also have r, dr, d theta, dz. And let's start filling in the pieces. So I'm going to just kind of go forward with this, and I'm going to hit a snag and hopefully illustrate a point, a bit of a teachable moment here. R is going from 0 out to the radius 4 everywhere. Theta is going from 0 to pi over 2 just to get that first quadrant of the circle. And what's z doing? Z is going from 0 up to x. That's bad. We can't have a variable in the last integral because that x never really gets resolved by the integration process. So that last integral, that outer integral, always has to be a constant to a constant. So this suggests that we have to change the order of integration in order to fully resolve this integral. So I'm going to get rid of this integral, and let's move this piece out a little bit, and we'll move that z integral, make it the first integral. And that's going to require me to shuffle around a little bit out here too. Like that. Perfectly legitimate thing to do. Fubini's theorem says that's okay. So now I can go from 0 to x, right? Well, hold on a minute, Schuler. There's no x's in cylindrical coordinates. What do? We replace the x with the appropriate cylindrical transformation, r cosine theta. So mxy looks like this. Let's delay calculating that integral for a minute, and let's do myz. Those are the two moments that the problem is interested in. The limits of integration are exactly the same. So we're going to go around. Looks like I lost a little bit of my, yeah, I'm not really sure what happened there. Okay, this upper limit in R should be 1, 0 to 1, because it's dz, dr, d theta, and then the upper limit in theta should be pi over 2. I'm not sure what happened in the copy and shuffle process. Now, the integral stays the same. 0 to pi over 2, 0 to 1, sorry, the limits stay the same. 0 to r cosine theta. Now, we're doing myz. The missing variable is x for that moment. Everything else is the same. The density function, the r from cylindrical coordinates, dz, dr, d theta, like that. And again, we have that x problem. We can't leave that x there. We have to change it to r cosine theta. I'm going to check my notes here real quick, make sure I'm not leading anyone astray here, and it looks like we're okay. Oh, wow, I'm glad I checked my notes. The r variable is not 0 to 1, it's 0 to 4. 0 to 4. The radius of the circle is 4. Okay, we have the integral. We can't really do much here in terms of separating things out. It looks like we could pull out the r if we wanted to. No, not even the r. We've got an r here, a theta here, and of course dz is yeah, even dz is going to introduce a factor of r cosine theta. Okay, so let's jump over to Sage and finish this calculation up. In problem 345, the variables I'm using are r, theta, z, and that constant of proportionality. I'm going to assume the constant of proportionality is positive just because it might make life easier. The moment about the xy axis is, of course, the density function, which is a constant, comes all the way out. This triple integral of z times r, right? Z times r, the k came out. Z goes from 0 up to r cosine theta, r 0 to 4, theta 0 to pi over 2. Similarly, myz, exactly the same as this, except the z here, if you look closely, has turned into an r cosine theta, aka x. And then once I've computed these two quantities, I'm going to print them out and we'll see exactly what they are. Mxy is 8 pi k, myz is 16 pi k, 8 pi k, and 16 pi k. And what are we asked to show? We're asked to show that mxy is half the moment of myz, and in fact that's the case. Mxy is 1/2 myz. Check, we're done. All right, last exercise. The average density of a solid can be computed by integrating the density function and dividing by the volume. So we're asked to do this if the density of the unit ball is given by this expression. We're going to use Sage to find its average density. All right, the average density, rho average, is the integral over the unit ball. All right, what's the unit ball? I think we've got a sphere here. We should probably use spherical coordinates. The unit ball, rho goes from 0 to 1, phi goes from 0 to pi because it's the entire unit ball from the North Pole all the way to the South Pole. And theta goes from 0 to 2 pi because it's the entire ball all the way around. We want to integrate the density, and the density is given by this e to the minus x squared minus y squared minus z squared. If you look closely at this, this is e to the minus x squared plus y squared plus z squared, and you should recognize that as rho squared. So this is e to the minus rho squared. We're doing a spherical integral, so dv here becomes rho squared sine phi d rho d theta, sorry, d phi d theta. Got to pay attention to the order of the limits of integration here. This is a hard integral. In particular, the rho integral is essentially impossible. It's going to introduce something called the error function, which is something that you see in statistics, because in statistics they're constantly integrating Gaussians, and this is basically a Gaussian function, and there isn't an antiderivative that we have convenient access, right? The antiderivative of sine phi is, of course, minus cosine phi, and then we can plug in limits. Nobody knows what the antiderivative of e to the minus rho squared is. It doesn't have one. And so we introduce this thing called the error function, which is just the antiderivative of e to the minus rho squared, and then we know things about it. So we're going to jump to Sage, long story short. And this is the average density. What I've got written here is the mass. We've got to divide by the volume of the unit sphere. Remember, the unit sphere has radius 1, and that the volume of a sphere is 4/3 pi r cubed. In this case, the volume is going to be 4/3 pi, so it's 1 over 4/3 pi because we need to divide by the volume of the set over which we're integrating. And then we'll turn this integral over to Sage and let Sage do its magic. So we're integrating, we find the mass here. It's a triple integral. Here's the integrand, the density, and then rho squared sine phi, which just is the factor that we need to include for spherical coordinates, and then the limits 0 to 1, 0 to pi, 0 to 2 pi. And let's integrate that. And as I warned you, the error function appears in a mysterious way. We're not going to worry too much about that. And then I asked Sage to give me a numerical value for that mass, and it turns out to be about 2.38. And then the average density is the mass divided by 4 pi over 3. And that works out to be about 0.57. So this works out to be about 2.38. I'll put a squiggly equal sign since it's not exact. And this is in turn approximately equal to 0.57, like that. And that's it. All right. Just a reminder, all the exercises are on the table at the end for figuring out this new material, with the exception of 321 through 332, which concern moments of inertia, and I'm de-emphasizing that, and then 340 and 355 for the same reason. They both involve moments of inertia. When you're finished, hop over to WebWork and take the assessment for Chapter 5, Section 6. Good luck and thanks.